So the presentation is from Cong T, Nguyen. He is from the Faculty of Engineering and Information Technology, University of Technology, Sydney. The title of his research is Beneficial Investigation of Extended Range Electric Powertrains with Dual Motor and Multi-Speed Transmission. Okay.
Hello everyone, I'm Nguyen from University of Technology, Sydney, Australia. I'm very happy to be here and present my study to all of you. My research topic is beneficial investigation of extended range electric powertrains with dual motors and multi-speed transmission. This is a part of my PhD study at the University of Technology, Sydney. I will start with the introduction section. As you know, with the current limitations of electric batteries, extended range electric vehicles can obtain more advantages in comparison with pure electric vehicles. The first advantage is low manufacturing costs because EREVs require smaller batteries. Furthermore, with the inclusion of engine and fuel tank, the EREVs can have unlimited driving range. The battery can be charged at home, so there is no need of public charging station. The engine also can help to charge the battery on board, so the battery is avoided from being exhausted, so it helps to increase the battery lifetime. Next, considering the transmission system of in electrified vehicles, so compared to other kinds of automated manual transmissions, AMT can obtain additional benefits including high dynamic ability, high transmission efficiency, and low manufacturing costs as well as low maintenance costs. Moving on to consider the motor inputs. So recent studies have demonstrated that dual motor inputs help to improve energy efficiency by inclusion of multiple modes. From this analysis, this paper will focus on the extended range electric vehicles equipped with AMT and dual motor inputs. The first investigated configuration is named as Dual Motor Series Powertrain DMSP. Its configuration can be divided into two subsystems, electric propulsion system and range extender. The electric propulsion system here includes two drive motors and 4-speed AMT. The range extender is formed by an engine generator unit. The second investigated configuration is named as Dual Motor Parallel Powertrain DMPP. The DMEP has a same electric propulsion system in comparison with the DMSP. However, the range extender here connects the engine to input shaft through a frictional clutch. The first configuration, DMSP, can operate in totally 6 modes, 3 EV modes and 3 Series H EV modes. The EV modes can operate with motor 1 only, motor 2 only, or 2 motors at the same time. In Series H EV mode, the engine turns on to charge the battery or to drive the vehicle directly. The second configuration, DMPP, can operate in totally 8 modes, including 3 EV modes, 1 engine mode, 1 Series H EV mode, and 3 parallel H EV modes. Here, the EV mode and Series H EV mode are the same in comparison with the configuration DMASP. However, in engine mode and parallel H EV modes, engine is connected to the input shaft to drive the vehicle directly. Next is the table of powertrain specifications, with the same parameters are applied to all components of two investigated powertrains. And then next are operating maps of the motor, generator, and engine. Then the mathematical models of two investigated powertrains are established, including 4 main models: powertrain system model, vehicle dynamic model, battery model, and engine model. In the engine model, fuel consumption and gas emissions are calculated based on the lookup table method. Gas emissions here include hydrocarbon, carbon monoxide, nitrogen oxides, and particulate matter. And here are the emission maps of the engine. In order to improve the energy economy of the investigated powertrains, an energy management strategy is developed here. So based on the vehicle speed and vehicle demand power provided by the driver model, the energy management strategy will determine the control inputs for the vehicle model. Here the developed energy management strategies consist of 3 parts: gear shift schedule, motor torque allocation, and model predictive control-based energy management of battery and range extender. The gear shift schedule and motor torque allocation aim to improve motor efficiency while reducing the number of gear changes. Furthermore, the model predictive control-based energy management of battery and range extender aims to use the electricity from the battery reasonably. For example, if the travel distance is short, so only electricity from the battery can be used to drive the vehicle. Conversely, if the travel distance is very long, so both electricity from the battery and fuel will be used to drive the vehicle. The details of the developed energy management can be found in the references provided here. Then the advantage of 2 investigated powertrains will be evaluated in comparison with a conventional single-motor series powertrain under the driving cycle Chinese city bus cycle. According to battery state and travel distance, there are 2 case studies. The first case study is electric driving condition. Under this condition, the engine will turn off. The motor drives the vehicle with electricity provided from the battery. So we can see here figure A and figure C are gear state and motor torque of the single motor series powertrain SMSP. Figure B and figure D are gear state and motor torques of the dual motor configurations DMSP and DMPP. From figure E, we can see that the dual motors, motor 1 and motor 2, work with higher efficiency than the single motor, motor 0. As a result, the DMSP and DMPP reduce electricity consumption significantly in comparison with the SMSP in figure F. The second case study is hybrid driving condition. Under this condition, both engine and motor will operate to drive the vehicle. We can see here figure A, B, C, and D are the torques of engine and motors of all configurations. Figure E is the battery state of charge, so we can see all the final values are very close to the minimum of 0.3. Figure F is the comparison of fuel consumption. So the fuel consumption reduced in the following sequence from SMSP to DMSP to DMPP. Figure G shows that with engine connection in series, the SMSP and DMSP allow engine to work with high grid efficiency. Conversely, with engine mechanically connected to the driveline, the engine of the DMPP has to work with a wide range of engine speed and engine torque. The simulation results of 2 case studies are summarized in this table. The performance index consists of electricity consumption, fuel consumption, and gas emissions. The improvement of the dual motor configurations are compared to the conventional single motor series powertrain. So here we can see the DMSP improve all performance index in comparison with the SMSP. The DMPP can reduce the fuel consumption further. However, this configuration generates much more gas emissions. in comparison to SMSP, including hydrocarbon, carbon monoxide, and particulate matter. In conclusion, this paper investigates the performance of two EREV configurations, DMSP and DMPP, analyzed powertrain configurations, and established mathematical models, developed a model predictive control-based energy management strategy. Simulation results show that the DMSP and DMPP reduce energy consumption up to 8.9% and 14.4% in comparison with the conventional SMSP. The DMSP reduces all exhaust emissions considerably, while the DMPP increases almost emissions except for nitrogen oxides. This is the end of my presentation. Thank you so much for your kind attention.
Okay. Thank you. Thank you, Professor Nguyen. Okay. Thank you, Professor Nguyen.
Thank you. Thank you.
So, is anyone have any questions? Anyone have questions?
Yeah. Can you hear me? I want to ask a question for the emission model.
Yes, I can.
Yes. Your emission model is quasi-static, right?
You mean emission model?
Yes. How accurate is it?
I use a lookup table to calculate.
Okay. So you only consider the steady state conditions for the emissions, right?
Yeah. Just use the map to calculate from the motor speed and engine speed and engine torque. From that, we based on the lookup table to calculate the value of emission at each point of time.
Yes, but as you know, during the powertrain transients, the emissions are quite different from the map, you know.
Yeah.
So you consider a diesel engine, right?
Yeah, diesel engine.
Yes, actually, it's very challenging to accurately model the, NOx, nitrogen oxides emissions. So I'm not sure how accurate of the emission model it is. Yeah. So So you only use the simulation, right?
Yes, simulation based on the results.
Maybe in the future you can consider some, hardware in the loop testing to validate your results. Okay.
Actually, it's in my research. I mainly focus on. Actually, it is a part of my PhD thesis. So in my thesis, I mainly focus on the efficiency and fuel economy. So the emission is only a part, a very small part of my thesis. So in the future, actually, according to the succession, I will consider it more carefully with the more real model. Yeah, because as you recommend, the emission is change differently depend on the condition, right? Yeah.
Yes, thank you.
Yeah, thank you so much.
So, Professor Nguyen, I have a question. If the dual motors and the different extended range structures are used, parameters of engine, motors, and transmissions should be rematched. So, if it should be more reasonable to compare after getting the optimal parameters. Do you have any viewpoint about on the above topic?
So the question is about the parameter optimization, right?
Yeah, it should be more reasonable to compare after getting the optimal parameters.
Yeah, actually the parameter here is already optimized. But I'm not present the parameter optimization in this research. So parameter optimization is also was done but it's not. I'm not present here because the limitation of the paper. Yeah.
Okay. Thank you.
Thank you so much.
Professor Nguyen.